Hello everyone. The stream got and the stream stopped. My internet was not stable. It stopped. Now, that would be interesting. All right, so I don't know when it cut off, but I was just trying to say I'm going to use the most naive way to solve this problem. I'm just trying to see how do we detect overlap. So I say if the start of the new block is inside any of the old block, or the end is inside any of the old block, then it is considered a overlap. So we say if this is true, then we're going to return false, right? Return false. Otherwise, we can say when it's all done, self.booking start append, start end, and we return true, right? Actually, I think we can make this even easier. I don't even have to do this. We'll just go through this. Like if it's nothing, then we'll always do it. And then that's it. Let's take a look. O(n) squared. Yeah. Doesn't look promising actually. Let's try this. Pending, judging. Oh, we got a wrong answer. The logic is not right. How? We append. There gotta be some case. So the end. So for the start, like we have a range already. I have a start, and the start touch the s, because the start can touch the end, right? The start can touch the end, so the start has to touch the s and everything inside. Then that's a false. How about the end? Well, the end. Oh, the end actually can touch. So I think it's actually this way, because the end is not inclusive, right? So we can touch s. So we'll try it again. Pending, judging. Oh, got a wrong answer again. I think it's here, because the end, if I end it here, hold on, the end has to be when we overlap, right? When we overlap on the end, the end can touch the start. That's fine. The end, if it's larger than the start, then that's a problematic. Oh, hold on. I know what case. It's a case like this. I think I misconsidered this case. Like say 1, 2, and 0 and 3, right? And it's not including anything. This is interesting. So what I have considered here is overlap, but this one is not overlap. This is like a completely enclosing, right? Or the other way around. We have a 0, 3. Now we have a 1 and 2. So I'll just put more. So if this, right, or this, or actually, or start is larger equal to s and is smaller than e, right? That's enclosing. And can be equal to e. Actually, that doesn't really matter. But isn't this the same case as this? Yeah, this is the same case, so that's not the case. The case should be this. The start is smaller than s, and the end is larger than e. That's the one, I think that's the one. The end is larger than E? Well, the start is smaller than S, and the end is larger than E. So larger equal or larger? Larger equal, because we can have equal, because here is not, this is small, right? So let's try this. All right, one more time. Pending, judging, accepted. All right, so this is just a very, very naive way, and I expect the runtime to be pretty terrible. All right, the runtime would be pretty terrible. So I'll say this is a naive on squared solution. The trick is with how to detect overlap, but we didn't make any effort to improve on the data structure for storing the ranges. So I dread to see the actual runtime. But a pass, well, we can pass because there are only 1,000 booking calls. So on squared is still tolerable. So this one gives us 1,128 milliseconds. Hold on, 1,128 milliseconds, or a 15% ranking. Yeah, so we know that this can be solved this way, but definitely that is not where we want to end up with. So now let's think about how to improve on it, right? So when we talk about improvement, we just want to make it faster. And the way to make it faster is to use a different data structure, right? We cannot go through every single time. There got to be some way, right? So let's say we are given some ranges, and now I have a new range. Right now I have a new range coming in. What is the fastest way to know? Let's say we also know, but I think if we do sorting, it's gonna be problematic because we cannot keep the order. Right? We need to keep the order. Otherwise, we can speed up on some instances, right? Like when we do not insert, we can be very fast. Just log in, then we can search for it, and then we're good. But if we want to insert, that is going to be slow. Actually, very slow. So we have to move on. No, not very slow. It's just the same. So we can speed up a little bit. We actually try that idea. Basically, we're gonna sort the. Can we just sort one of them? I mean, we can sort. We can put them like tuples, right? Tuples. Tuples. We sort tuples based on. Doesn't matter first or last. It doesn't matter. And then when I have a new one coming in. Oh, if it's a tuples, how do we do binary search? Can bisect handle tuples? That's an interesting question. I do not know. So let's try it. So let's say we have tuples. 1, 2, right? Let's say 4, 5. I say 4, 8, and 9, 12. Right? So this is, and then when I say import bisect, I say bisect dot bisect left A let's say we're going to sort a 3 to 5. Let's see what we're going to get. Oh, we can use this 3 to 5. Then we say bisect left 0, 1, so we can insert here, right? So then we know which one, because it's sorting based on the front. So now what we can do is check this value and this value, see if these two overlap, right? And then we're going to check this value and this value, see if these two overlap. If none of these overlap, what if I have something in the middle? Well, if I have something in the middle, that means so check this and this, right? So this has to be smaller than this. Yeah, then we just need to do one check. So this is not good. How about insertion, right? Let's say if we do 3 to 4. 3 to 4, we're going to do 3 to 4. It gives you 1 as well. And we still want to insert it. So what we do, a dot insert 1, 3, 4. Yeah, now we insert it into it. I think it'll be faster than this one, but still, that's worst case scenario is still pretty bad. Anyway, but give it a shot. So when you import bisect, right? Bookings is still, so this is still O(n) squared, but with time saving when a failed booking happens, right? So what we're gonna do is we can go with if not, right? If not self.bookings, and then we say self.bookings.append start and, right? And then return true. Otherwise, we're going to say index equals self.bookings. No. Bisect left. Bisect left. Self.bookings start end. Right. This will give us the index. So once the index is ready, it's going to be the one to the front, right? The one to the front. So we're gonna check. To the left and to the right, right? So when you check to the left, we say if index is larger than 0, right? If index is larger than 0 and self.bookings index minus 1, 1, that's the AND. If this AND is larger than start, that will be returned false. If index is smaller and self.bookings what n index, yeah, self.bookings index 0, that's the start of the next one. If this one is larger or equal, we can equal larger equal to n. No, it's not, it's smaller than n. Yeah, if it's smaller than n, there's nothing in between, right? So we check the front, check the end. this is my front, right? My front encroaching the previous one, that is a fail. And then I'll check this one. So if my AND is encroaching on this one, right, which means the start is smaller than the end, then we're going to return false as well. Neither, self.bookings.insert, right, self.insert start and add position index. Oh, my streaming gets really slow again. Anyway, so this one, let's take a look. Yeah, let's finish this. Okay, run code. This one shall be fine. Yeah, submit. Oh, this one's faster. Okay, we pass. And this one shall be faster. Oh, this one's much faster. Well, it's we get 200 millisecond runtime, and it's at 90% ranking. Well, apparently the test cases contain a lot of failed bookings, and this solution takes advantage of that fully. But I'm still not happy. I'm still not happy with it, because in the worst case scenario, where the bookings are given in a reverse order, then this solution runs in ON, right, in ON squared. So it's still not good. But I don't know. I mean, we need to keep the order. Is there another way? Arrange. Like given a value, and given a value, can we immediately tell what range it is in? Well, if I have a tree data structure and the beginning is just the smallest, so we have range, let's say A, B, C, D, E, F, right? They're in range. And then the top range will be AF. So if anything comes in, like the starting point is outside, is to the right of AF, we can immediately do it. If it's inside, and then we split, right? How do we split? Let's say we split in half, right? We're splitting in half. So this is going to be from A to something like half, right? And then if we split in half, then we will contain part of the range and part of the other range. So when I'm trying to see it, like the start is in between, so I want to see where the start lands, right? So the start is in between of this, and then let's say the start are larger than half, is smaller than half. Let's try it. So let's say we have what, 1, 1, 3, 5, 10, and 12 to 14. So I say the top node have the range 114, right? The top node is 114, and what type of information should we include in this? 114. Oh no, let's go. Let's just split if it's 114. That's 15. That's 7. That's 7 and 8. So we're gonna say one of them is going to be 1, 7, and the other is going to be 7 to 14. All right, and 1, 7 will contain. Now we don't do contain because 1, 7 is not containing anything. So we're gonna keep splitting. All right, 1, 7. We're gonna keep split. That's split into 1, 3, right? 1, 4, and 4, 7. 1, 4 contains a range, so we can say the range is 1, 3, right? That's it. No other range. 4, 7 contains another range, that is 5. No, that contains 5 to 7. Right? That contains 5 to 7. 5 to 7, but no more. Now 7 to 14, that's 21. So equal 10. Say it's going to be 7 to 10, and 11 is 10 to 14, right? And the 7 to 10 contains 7 to 10, right? Okay, 7 to 10. We have 7 to 10. That's the range. And 10 to 14 contains 12 to 14. That's another range. So that's how the range goes. Right, given this, now we want to insert a new one. Let's call it from 4 to 6, right? Let's call 4 to 6. So we go with 4, right? We'll go with the start. So 4 comes in, 114 is going to do the left branch, 4, and then 1, 7, right? 1, 7. So 4 is going to go to the right branch for 1, 7. So 4 comes here, right branch, and in here we do find that we have a range, right? We have a range. So we say 4 is smaller than the range start is 5. So we're good, right? So here we find it, 4. Now we need to go with 6. Right? We're gonna go with 6. Yeah, so basically we split up, right? We'll go with 6. So 4 is good. And 6. Right, so 4 is landing in between two ranges. That's good. So we go 6. And 6, we go also to the left branch. And then we go to the same, 4 to 7. So 6 is stuck in between. And now, oops, we're in between. So 6 is no good. What if we go 4, 11? Right? If we go 4, 11, and 11 is going to the right branch, right? Right branch 11 is going to go all the way to the right, and we hit 11 is also not enclosing. So 11 not enclosing anyone. But how do we tell that 11 is going to well, it's because 11 is adjacent to 12, right? And 4 is adjacent. How do we know there's nothing in between there? So 4 is good. 11 is also good. But they are encompassing two ranges in the middle. How do we tell there are two ranges in the middle? How do we tell? Well, we can tell because from 4, right? 4 is not in any range, so we can see that the next range after 4 at least extend to 7. But now you are at 11, right? Then you were wrong. So that's good. We can do that. How about inserting? Let's say we want to do 3 to 4. Right? We can do 3 to 4. So how do we insert a new one? 3 to 4. Again, 3, we'll go to the left branch, go to the left branch. So 3, which is good. So 3 is here, we're good. And then 4 is actually going to go to the right branch. 4 is going to go to the right branch. Hold on, 4. Yeah, 4 is going to go to the right branch. And 4 is the end, which is good, right? 4 is good. But then we're having a cross or crossing, right? And we also have so we do not want crossing. Now we want, what do we want? We want each range to contain only 1. Then we just have to keep splitting, right? We have to keep splitting. So 3 to 4. How do we split? So from 3 we say, yeah, we're going to keep splitting. So when 3 comes in, 3 is good on the left branch. When 4 comes in, 4 is good on the right branch. Then what? Then I say the left branch needs to split. Okay? So like we consider this is a good case. So we say, but they're on different branches. So they're not on the same branch. If they're on the same branch, on the same node, then we split. Yeah, we always have to split. Like every time we get a new one, we have to split. So we split 1, 4. We split into 1, 2, and 2, 4, right? So 1, 2 will contain 1, 2, 3. 1 to 2. 2, 4 will contain 2 to 3, and 3 to 4. Huh. 3 to 4. Okay, 3 to 4. And then we have 2, so we keep splitting, right? We keep splitting. 2 be 2 to 3, and 3 to 4. 2 to 3 is its own, right? 2 to 3 is its own, and 3 to 4 is its own. That's my work. It's complicated, but I think inserting is just O log n, right? We're doing levels. We can do O log n to insert. Just every time we insert, we just split up. We make sure that each node contains at most 1. Right? Each leaf node contains 1 range. Alright, that's the idea, but do we want to try it? Maybe we can. I mean, we can use just a dictionary. Now let's create a new thing. I don't think this one will be faster, but it will be interesting to write. not sure if this idea will actually work, but you can write it. So we're gonna say class, we call it a range node, right? And then def initiate self. So what do we have? We have a self dot left, self dot range equals so this one is going to be left range int, right range int, right? And this is going to be left range and a right range, right? And then left range, right range, and then self dot left is none, self dot right is none. Okay. So self dot bookings is going to be an empty node, right? Initially it's empty node. So we say if not, if self dot bookings is none, then self dot bookings equals, oh, but if we have something more, then when you create a new node, yeah, that's fine. So self dot bookings is going to equal to range node start end, right? And then return true. Otherwise, now we need to check. So the ideal is the top is always going to be the maximum range. So say if start is larger or equal to self dot bookings dot range 0, no, range 1, right? If that's the case, now when you create a new node, right, then we say new root equals range node. The left is going to be self dot bookings dot range 0, and the right is going to be end, right? And then new root dot left equals self dot bookings, and a new root, yeah, and new root dot right equals range node start and end, right? And then we say self dot bookings equals new root, then return true. Okay, and then if and is smaller, right? And is smaller or equal, okay, smaller or equal to self dot bookings dot range 0, right? That's another case. So basically I can copy this. Similar. And say new root is going to be, this is going to be start. This is going to be self dot bookings dot range 1. Left is going to be this, and the right is going to be this. And then okay, these are two edge cases. Now we are handling, oh wait, it should be over, like in passing. So if start left is larger than this, and so start left is larger, oh, that's actually fine. Start left is fine. Start left is larger than, it's fine. The end, oh, this is fine. This is fine. So now we're dealing cases that's not, then we're gonna go look for the left. right? And then look for the left. So look for the left. We're gonna go through, and this just feels very complicated. And if left and right, I say if start is smaller than and equal to the start, and then end is larger or equal to, yeah, this is the total range, right? So if it's inside, then there's a possibility. If we do this to this, then that's an overlap. That's too convoluted. I don't know. I want to check the answer. This feels like very convoluted to me. Hold up. Let's try it. If this is smaller self.bookings.range 0, and we're handling the overlap and larger than equal to self.bookings.range 1, right? This is say my current is overlapping the entirety of the current bookings, and that's going to return false, right? If it's smaller equal to the range left, and end is larger equal to range 1, and that is, but if we move inside, oh, hold up. So we say this end is smaller. There must be overlap, right? If start is smaller than this, then that means if start is smaller than this, that means the end, we didn't do this, right? And the end is not. So we just say if start is smaller than or end if start is small. So we handle these two cases, right? We handle the good case. So now the only case is in between, right? In between. So I think it's going to be if the start is smaller or equal to this, and the end, no matter where you are, it's going to be overlap. So I think if the start is this, it's going to be overlap. Or the end, or the start is smaller. So if start is smaller than this, if start is smaller than this, then the maximum range, right? Then that's going to be overlap. And let's say start is larger, as we already handled this. So if the end is larger, yeah, if the end is, so if this or the end is larger than, but the end can be equal to, so it has to be larger. So the end is larger than this, right? Because we already handled this situation. So if these situations happen, then we false. Now we're gonna go to the nitty gritty. Now we have to, now the start and end are both inside, right? Then we need to go start. So basically, the range is this, right? And then we got the first one, So we're gonna split. It just feel more convoluted. All right, I don't want to keep going down this way. It just feel very convoluted, unless the official solution has something similar to this. I'm gonna go for it. Brute force accepted, or balanced tree. Yeah, look at this. A balanced tree. This is the one. This is the one. A balanced tree. This is, yeah. Oh, hold on. I don't have to check. I checked way too much. How much did I check? Hold on. We only need to check the term false. 0 is smaller than end, and start smaller than. If the start is smaller and the end is larger, then I'll return false. Hold on. S is smaller than end. Wait, no, S is inside. If any range S is smaller than the end, and the start is smaller than the, what the heck? S and E, right? We say if start is smaller than E, and is larger than S. Start is smaller than E, and is larger than S. Then we return false. Okay, so and is larger than this, yeah. If start is smaller than E, yeah. How about the encompassing? Oh, it hits that as well. Oh wow, it hits that as well. Hold on, let's see again. And larger than E. If n larger than E, n must be larger than S. If start is smaller than S, then start, so this and this can be combined into start smaller than E. This and this combined can be n is larger than S. It could be done simply, much simpler. Alright, so I don't like this one. We're going to redo it later. But here, this one can be simplified. Let's just say the if condition can be simplified as if start is smaller than E and n is larger than S. Yep. Start is smaller than the end. Yeah, if start is smaller than the current end, right? And then the end is larger than the start, because n is smaller than the start, that's a good thing. Or n is larger than the start is larger than E. Yes, that's correct. Okay. O(n) squared, that's bad. We got lucky with this. If we intend our events in sorted order, we could check whether an event could be booked in O log n time. Yes, just like this. Binary searching, but also have to insert. Yeah, that's the problem. Insert the event. How do we do that? We need a data structure that keeps elements sorted and it supports fast insertion. In Java, a tree map is perfect. In Python, we can build our own binary tree structure. I think I was trying to do that, but I feel like it's convoluted. The keys are the start of each interval and values at the ends of those intervals. And inserting the interval, we check if there is a conflict on each side with neighboring intervals. Alright, the get previous, smaller, smaller, smaller than next. For Python, we will create a binary tree, a node. Each node represents some interval, while self.last represents nodes that are smaller or larger than current node. Okay, let's see. The node, it does have to create a new node. Start, end, both are none. Okay. Insert. If node insert, what is insert? A node dot insert a new node. Okay, so we say def insert node dot start. The new node dot start is larger than self dot end. Okay, if not self dot right, self dot right. Okay, that's good. Yeah, and if not, so if node larger than, then we do this. If they have self dot right, then we need to go self dot right dot insert node. That means my current start is larger than the end of the current node, and if the current node do not have a right child, I can insert it right there. If it does, then means I have to go to the right child to do the insertion again. That is correct. If node.end is smaller equal to self.start, that's just the same thing. Yeah. Else return false. So I do two recursions, right? And then that's the case right here. That's the case right here. Start smaller than e and end larger than s. So if these two do not satisfy, then that's the end. So we only insert if the start is larger than the end, and we can go to the right side. Or if the end is smaller than larger than the start, we go to the left side. If the start is smaller than the end, right? If the start is smaller than the end, that's fine. We can go to check the end, and the end is larger than the start, right? The start is smaller than the end is larger than the start. Then that is the problem. Start is smaller than the end is larger than the start. No matter what you do, and then we return false. That's how you do it. Search event is O1 login, insert is O1. Yeah, that's correct. If the input is highly ordered, then the BST is likely to turn into a list. This is correct, right? Yeah, and if the input is sorted, but the input is sorted, how do you balance a tree? Bookable means we find an interval and know where the new one should be placed. Right, if it's enough to maintain a list accessible by index and do a binary search. Once the event becomes bookable, we find an interval and know where the new one should be placed. But you still have to place the new one. There are not many conflicting events. What is the time constant for average? Yeah. Hey, what do other people say? Tree map. Overlap. Yeah, this is just check everything. And only check 2 books start right before and right. Keep the intervals sorted. You have to sort every single time. A tree set, a tree map. Order set, order map. Oh, this is insertion. Python doesn't have it. Binary search tree. You have to do it this way. Tree is not self-balancing. Yeah, oh, yeah, that's ON. That's ON. Average, no, worst case is ON. Average is O log n. That's true. The binary trees, they're not balanced. Can you self-balance it? Yes, you can, but it's hard. Like we need to change the root if you want to self-balance it. Binary search tree. All right, let's write it. Yeah, this is much better than how I had imagined. So class, I'm going to call it range node. Right, I'm going to call it range node. Range, yeah, I just call it node. BST node, right? Def init self. So we have start and, right? Start of the integer and going to be an integer. And self.start equals start. Oh no. Self.end equals end. And self.left equals none. Self.right equals none. Okay, but now we have to do insert. This is something I never used before. We have the insert function. Another node, which is also a BST node, right? So we have another node. Yeah, we try. Don't look at this. I'm trying to write this out. So when insert, so we are doing binary search. We can reach the node, right? And then we need to insert. So we say we're going to check if we can. So we say the only possibility we can is if node dot end is smaller or equal to self dot start, right? That means we can do so node dot end is smaller than equal to self dot start, so we can go to the left side. We say if not self dot start, not self dot left, then self dot left equals node, right? And then return true. So the insertion is actually going to return a Boolean value. If not, if the left is already, then we need to insert. That means we have a left, so we need to keep going left, right? We need to keep going left. So current end is smaller than the start, so we keep going left, and we have something more. The start will be smaller. So I'm going to say, just return self.left.insert node, right? So we insert node on the left. So we do the same thing. We say self.start is larger equal to a node.start, larger equal to the end. Now we're going to go to the right. Then right equals node. or we can say self.right.insert is elif, and then that's actually not, doesn't have to be because we already return. In this case, then we just return false, right? Now we're gonna do our thing. All right, so self.bookings equals none, right? Let's say if not self.bookings, then self.bookings equals BST node start and return true. Otherwise, then we need to see. Otherwise, we just say self.bookings.insert BST node start and, right? Just try to insert it and when it return. Yeah, when you insert and then when you check. If it's bad, if it's good, then we're gonna insert. Okay, let's take a look. This is my effort. Alright, let's try the test case. BST node is not defined. Alright, let's not be fancy. Let's just do this. Okay, try it. Alright, yeah, it's fairly fast. It's fairly fast. So this is the official binary search tree solution. I was thinking about a tree data structure to handle faster insertion while maintaining the faster insertion while maintaining the sorted order. But the scheme I was cooking was too convoluted. This is the correct way to construct a tree for this purpose. Average runtime is O log n, O and log n, right? O and log n. Average runtime is O and log n, but worst case can still be O n squared. And this one we run at 264 milliseconds. All right, that's it. I mean, it was not too hard because the brute force works, and we also kind of cheated with this solution. I kind of cheated with this solution, taking advantage of the fact that there are way more collisions than actually insertion. But this is something we need to brood over a little bit more. It's a very good data structure to think about. All right, that's it. That's it for today. I'll see you guys tomorrow. Adios.